All right, let's just dive right in. For this explainer, we're going to be digging into Chapter 8, which is called Experimental Research and Levels of Evidence, and it's from the book Research in Communication Sciences and Disorders. Basically, we're going to build a toolkit so you can tell the difference between some solid, maybe even life-changing science and all the junk that's just out there trying to sell you something.
I mean, you see this stuff everywhere, right? Claims that this one little thing is going to change your entire life. So how do we actually separate the real breakthroughs from the total BS? Well, it all comes down to the quality of the proof. And today, we're going to look under the hood to see how that proof gets made and how you can spot the good stuff from the garbage. Okay, so let's get into it. At its core, good science is all about one thing, proving that A causes B. Not just that they hang out together or happen around the same time, but that one thing directly causes another. And to prove that, you really need a fair fight. The rulebook for that fight, that's what we call research design. It's the whole setup that makes sure the results aren't just some lucky punch. Now, in every single experiment, you've got two main players. The independent variable, that's the thing the scientist is messing with, the new drug, the therapy, the app. You can think of it as the potential cause. Then you have the dependent variable. That's the outcome they're measuring to see if anything actually changed. That's the effect. So, does this new fertilizer, the independent variable, make the plant grow taller, the dependent variable? It's really that simple. So here's the thing. A whole lot of stuff can go wrong and totally wreck an experiment, giving you a completely bogus result. The textbook calls these threats to internal validity, but I think it's way easier to just call them experiment killers. These are all the sneaky alternative explanations that can fool us into thinking a treatment worked when, it really didn't. Let's meet the usual suspects. First up is history. And no, this has nothing to do with the past. It's all about something else that happens during the study. So imagine you're testing a new reading program for kids, but halfway through your study, the teacher, completely on her own, starts this awesome new reading game. At the end, the kids' scores shoot up. Was it your program or was it the teacher's game? You have no idea. That outside event just totally sabotaged your results.
Next up, we've got maturation. Oh man, this one is huge, especially when you're studying kids. People just change over time. It's natural. They grow, they learn, they heal. So if you give a kid with a speech impediment some new therapy for 6 months and they get better, was it the therapy? Or would they have just gotten better on their own as they grew up? Maturation is this powerful, invisible force you always have to watch out for.
Okay, this next one sounds super technical, statistical regression, but the idea is actually pretty simple. If you pick people for a study because they scored, say, extremely low on a test, chances are the next time they take it, they'll score a little bit higher. Not because of your treatment, but just because of random luck. They're regressing to the mean, or just drifting back toward average. This can totally trick you into thinking your treatment is a miracle when it was really just a statistical quirk. And believe me, there are more of these killers out there. Instrumentation is when your measuring tool itself changes, like if your scale suddenly gets less accurate halfway through. Selection. Oh, this one's a big one. What if the group getting the treatment was just smarter or more motivated than the group that wasn't, right from the start? And then there's mortality. It sounds dark, but it just means people dropping out of the study. Think about it. If all the sickest people drop out of your new drug trial, the drug is going to look amazing for the healthy people who are left. So yeah, a perfect, sterile, lab-coat experiment is really tough to pull off in the real world. Sometimes it's just not possible. But that doesn't mean we throw our hands up and give up. There are some really clever, practical designs that can get us some pretty good evidence. Think of these as the first rungs on the ladder, moving from just kind of guessing to actually knowing something.
These are called quasi-experiments, and quasi just means sort of. So you've got your treatment group and you've got a control group, but, and this is the key, you couldn't use the magic ingredient of random assignment. Maybe you had to compare two existing classrooms at a school. This is a massive step up from having no comparison group at all, but you gotta be really careful because those experiment killers, especially selection, can still totally sneak in and mess with your results.
Okay, so check this out. This is a cool approach called a single subject design. Forget big groups for a second. Here, we're focusing on just one person. So follow the line. In phase A1, we're just watching their normal performance. It's pretty low. Then, phase B, we introduce the treatment, and bam, their score shoots way up. But here's the real proof. In phase A2, we take the treatment away, and look, their performance drops right back down. That is some powerful evidence that the treatment was the real deal. And you can actually make that evidence even stronger. This is called a treatment replication design. You do that same ABA pattern, But then you add the treatment back in a second time in phase B2. And look at that, performance shoots right back up. You literally turn the effect on, then off, and then on again. It's like flipping a light switch, showing that you're the one in control. That is incredibly convincing stuff.
So, we've seen some pretty good methods, but what's the absolute best? What's the top of the mountain for proving cause and effect? Well, that would be the true experiment. You might have also heard it called the randomized controlled trial. This is the design that has a built-in defense system against most of those pesky experiment killers we talked about.
So what's the secret? It all comes down to one thing: random assignment. This is the secret sauce. It's what separates a true experiment from a sort of experiment. By randomly putting people into either the treatment group or the control group, you do everything you can to make sure those groups are basically the same from the very beginning. It just washes out all those pre-existing differences. So you can be way more confident that any change you see is actually because of your treatment, not because one group was just different to begin with.
This is the classic recipe, what the book calls the pre-test, post-test randomized control group design. Let's break it down. First, R, you randomly assign people to groups. Simple enough. Then, O, you observe or measure everybody to get a baseline. That's your pretest. Next up, X, you give the treatment to just one group. And finally, you do another O, observing and measuring everyone again with a post-test. If the treatment group improved way more than the control group, boom, you've got some seriously solid evidence.
Let's make this real. Let's say we have an app that claims to reduce public speaking anxiety. Okay, first, we'd randomly assign people to 2 groups. Then, we measure everyone's anxiety while they give a short speech. After that, the app group uses the app for a while, and the control group does nothing. Finally, we bring everyone back and measure their anxiety during one last speech. This is the kind of high-level proof you should expect for a new drug or an expensive therapy, because it does the best job of filtering out all the other possible explanations.
So, now that we know about all these different types of studies, we can finally start to rank them, because not all evidence is created equal. I mean, some of it is super flimsy, some is pretty decent, and some is just rock solid. Let's take a look at the big picture. This chart from the book really lays it all out beautifully. Think about it like this. The vertical axis, going up, is the strength of the evidence. Down at the very bottom, you have stuff like expert opinion, which is basically just one person's idea. As you climb up, the research designs get better and better, all the way to the top with the randomized clinical trial. The horizontal axis, going from left to right, is about the depth of the evidence. One single study? That's just one data point, but multiple studies all pointing in the same direction? That's way more powerful.
And what's at the very peak, the top right corner of that chart? That's something called a meta-analysis. This is like the final boss of scientific evidence. What researchers do is take all the best, high-quality studies on a topic, throw them all into a kind of statistical blender, and come out with one giant, super powerful result. It's the most reliable view we can possibly get on a topic. So when a meta-analysis says something works, you can be pretty darn confident that it actually works.
And there you have it. That's the hierarchy. It goes all the way from one person's opinion, climbing up the ladder to a huge meta-analysis. So the next time you see a headline or a flashy ad that says, "A new study proves something incredible," you'll know exactly what to do. You can ask the single most important question of all. Yeah, but what kind of study was it? Because now you know how to rank the evidence for yourself.